Hey everyone, and welcome to Awesome Sauce Mathematics video series on counting and probability. No, we're not necessarily talking about 1, 2, 3 counting, but instead applying combinatoric methods to solve problems.
Wait. Are you still there? Sorry for scaring you with big fancy words. Anyway, today we'll get started with a fundamental topic, using arithmetic to count. And it's certainly not as boring as it sounds. Throughout this video series, we'll approach new concepts by tackling problems that pertain to them in a fun and meaningful way.
We'll begin by talking about how to count the number of elements in a list of consecutive integers. For example, a set like 1, 2, 3, 4, 5. Our first problem is, how many numbers are in the list 5, 6, 7, 8, 9, all the way till 15? I encourage you to try this by yourself before referring to the solution, which we will present next.
You may have just counted from left to right and found that this list contains 11 integers. However, this process is quite arduous if the list asks for the number of integers between 7 and 999. This problem is a perfect opportunity to try a fundamental problem-solving technique, reducing a hard problem into something way easier.
We know that it's trivial to count the number of elements in a sorted set that starts with 1. Hence, we attempt to reduce the given set into a list of consecutive integers which starts with 1. We notice that if we subtract 4 from every element of our set, we are left with the sorted list 1, 2, 3, 4, 5, all the way till 11. So, yes, subtracting 4 from every element of the list, you're left with 1, 2, 3, all the way till 11. Obviously, this list contains 11 elements, so we have solved the problem.
In general, the number of elements in a set of consecutive integers from a to b is b minus a plus 1. See if you can prove this yourself by subtracting a minus 1 from all terms of this sequence.
That was a nice problem, but I think that you're capable of much more. Let's try another set counting problem, but with a twist.
Our next problem is...
count the number of multiples of 3 between 7 and 100 inclusive. Clearly, we can't use the same strategy that we applied in the previous problem, since not every integer between 7 and 100 inclusive is divisible by 3. However, don't worry, we're not doomed.
We see that the smallest multiple of 3 within our list is 9, which is 3 times 3. Since the previous multiple 6 is less than 7, we also notice that the last multiple of 3 in the sequence is 99, which is 3 times 33. Since the next multiple, 102, is larger than 100, hence our new list, 9, 12, 15, all the way to 99. How do we compute the number of integers in this list, however?
Referring to the previous problem, we manipulated the given list into something easier to work with by subtracting 4 from each element to reduce it into the sequence 1, 2, 3, all the way to 11.
In this case, we know that the set 9, 12, 15, all the way to 99 is comprised of all numbers that are multiples of 3. So we can divide each element by 3, giving us the list 3, 4, 5, all the way to 33. Using this set counting strategy we obtained in the previous problem, we find that there's 31 multiples of 3 between 7 and 100 inclusive.
No sweat. I think you guys can take more. Thus, at the end of each new topic introduced, we'll provide examples for you guys to work on.
Alright. Problem number 1, and unfortunately the only problem for this week. Count the number of integral perfect squares that are multiples of 3
between 7 and 100 inclusive. While this section was fun, often in counting problems, we're asked to calculate the number of ways a series of events can occur. When we're asked a question that pertains to this, we're working with independent events, since the outcome of one event doesn't dictate the outcome of another event. Once again, we'll explore this topic by doing problems that relate to it.
Our first problem is Bob, the evil mad scientist who's creating various potions to accelerate his plans for world domination. His potions are comprised of 2 separate distinct elements, snake scales and slimes. Bob has 5 different types of snake scales and 7 different types of slime. Compute the total number of distinct potions he can make.
We can approach this problem by listing out all of the arrangements for each different type of snake scales and slime. We use a computer program to do this. That's that the first number is the snake scale type, and the second number is the slime type. So let me show you the output of our computer program. So as I mentioned before, the first number is the snake scale type, and the second number is the slime type.
However, on pretty much all competitions, you can't use a computer program to solve the problem. However, I think we can better visualize each of these combinations by creating a chart as shown below, as we pull up one of our beautiful charts that Sai has made.
Thus, we see that for every choice of scales that Bob makes, the 7 choice for slimes, meaning that this 5 times 7 are 35 total combinations.
Sadly, we'll need to finish our lesson on independent events in the next episode. But before we leave, we need to leave you with a math problem. Here it is. At the AMC Alien Mathematical Conference, each of Mercury, Venus, and Mars needs to choose a delegate to send to the conference. If Mercury has 8 possible delegates to send, Venus has 7 possible delegates to send, and Mars has 6 delegates to send, find the total possible distinct combinations of delegates that 3 planets can consecutively send. Please try to solve this, as we'll be reviewing the solution in the next episode.
Thank you for watching. To stay notified about new videos that we create, please subscribe to our YouTube channel and share the video with anyone who seems interested in this beautiful area of mathematics. Thank you.